Binyomin Abrams is a senior lecturer of chemistry at the College of Arts and Sciences. He earned his PhD in theoretical physical chemistry from New York University. Professor Abrams has focused on developing novel approaches to teaching introductory chemistry that excites students across disciplines. Recent projects include the development of the Boston University Chemical Writing Program, the LA program, out-of-class activities to strengthen visual models for quantum concepts, and more. For his efforts, Professor Abrams was recently awarded Boston University's prestigious Metcalf Award for Excellence in Teaching. Please join me in welcoming Professor Abrams.
Truly a lot to live up to, I guess. Thanks for coming on Labor Day, guys. This is going to be really exciting. So the title of my talk this evening is Gone. Back, Gone, back. We're good?
Yep, that's good.
Okay, so we're talking tonight about the Bohr atom, 90 years of quantum mechanics, and why are we still teaching the Bohr atom? And really what happens when you announce a topic is you prepare and you realize that you don't have any desire whatsoever to talk about the topic that you've proposed. And they've given me 14 minutes and 53 seconds, and I'm going to talk until I'm done. And really what I want you guys to realize by the end of my talk today is, one, science is really, really cool. And if you're science majors or engineering majors, you probably already know that. And it's much cooler than you think it is, because there's a lot of depth to it that you're not going to see, or maybe you haven't seen, and hopefully you'll see. And the second thing is, it's not inaccessible to those who aren't going to be science majors. And if you're interested in things like quantum mechanics or quantum concepts, these are not inaccessible to you whatsoever, and you guys can learn it. There's going to be a core curriculum class on this stuff. Please look forward to all of that. So, it's the 19th century, and science is very deterministic. Laplace is famous for quoting that if you knew the precise locations, momenta, and forces on every particle in the universe, you could predict all times future and all times past. It was incredibly hubris, and that's how everyone felt. And the fact that at the end of the 19th century, the beginning of the 20th century, things started to creep into science where this no longer held true, this was frightening. Frightening to those who believed that science had to be one way. It had to talk about things, physical things that were always things. Then there was light, but light's light and things are things, and light is not things and things are not light, and things were, well, everything was somewhat okay. And then there were these concepts, uncertainty. And when we say uncertainty, I don't want you to be confused. This is not ignorance. There are things called ignorance in science, and that could also lead to somebody feeling uncertain, but that's not what we're talking about here. Uncertainty meaning there is no way to know, or my actions have consequences that are ill-defined or ill-definable. And this was very non-deterministic and very uncomfortable for a lot of people. You guys have experienced this. Any of you guys have electric stoves or been near an electric stove? Show of hands. Okay, so that's quantum mechanics in action. The fact that when you put energy, electricity through iron, it starts to glow red, not blue, not green, not yellow. If it starts to glow blue, you've done something wrong. And the thing that it glows red, and only red, that's weird. That's the way of the universe saying, hey, I prefer small packets of energy. Yes, you'll give me more electricity. No, I won't do anything with it. That's weird. Today we know it's commonplace because you all raised your hands. It's why we have fireworks. It's why we have all of the things around us. And yet, back then, this was scary and strange. The first person to try to give an answer for this was Niels Bohr. I should say a lot of people tried to give answers for this, and a lot of people failed. Bohr gave the first compelling answer, and I'm sure that you guys have all seen a diagram that looks eerily similar to this one, yeah? Right, we've all seen the Bohr atom. What's the Bohr atom? Look in the center, there's that very dense nucleus. That's Rutherford's nucleus. Bohr doesn't get credit for that. And you see the little green dots, those are your electrons. Don't worry, those are Thomson's electrons. Bohr doesn't get credit for that. What Bohr gets credit for is saying is that these things surrounding other things prefer, and for some reason that we don't know, have a predilection for staying in orbits around that nucleus at very fixed distances. And these are what determine the energies of the electrons. And when the electrons go from a high energy orbit to a low energy orbit, it releases energy, and that's the red light we see when we turn on our stove. Bohr, for his efforts, got the 1922 Nobel Prize in Physics, and no way, this is my disclaimer, in no way do I mean to belittle that achievement, and in no way do I think that we should take it back from him if we could. But it's time to stop teaching the Bohr atom. You see, Bohr knew that it was wrong. Bohr knew when he published his paper the first time that his model didn't work. Here's the Zeeman Effect, and if you haven't seen it before, that's probably because you're not a physics major, or you're not a chemistry major, or you didn't have a nerdy high school teacher, and I didn't have a nerdy high school teacher, so I never saw this. The Zeeman Effect's named after Zeeman, very famous guy. He took that atom and he put it in a magnetic field, and then he pumped it full of juice, and instead of releasing one frequency of light, it released 3. And Bohr's orbits couldn't handle that. So I want to be very clear. Bohr's model was flawed, wrong, and he knew it from day one. And yet, this is where we start. And the problem is, if we go back to our slide over here, our picture of the atom, it's things surrounding other things. This is our deterministic view of physics, of the world, just in a little bit a weirder way. And that's not what's happening. Now, the problem is, I wouldn't have a problem with teaching this in a history of science class, or maybe it would get a brief mention as we go through the curriculum in middle school or even in high school. But these are just some common images that we see from all around society today, where this planetary or Bohr-like model remains everywhere. We have a US Scout badge, we have some stamps, Canada, that's where I'm from. We see. Now, these are old, by the way. That's not. That is currently the Glasgow Science Centre's logo. Here is the Akron Science Fair logo. And here is the LA County Science Fair logo. All contemporary logos, all showing something that we've known is wrong since 1913, and oops, we forgot to tell you. Now, we live in Massachusetts. Massachusetts is known to be one of the best educational systems for high school in the country. It's number 2 in overall quality. It's number 1 in math and reading. And here is the MCAS, which asks you questions about which was the idea proposed by Niels Bohr. Who cares? He got it wrong. Okay, I don't mean to be so crass. Sometimes in the wrong, we eventually get to a right. But let me say, things are things is Bohr, and that's not reality. Here's another one where, again, I'm focusing on Dalton and Thomson and Bohr and Rutherford, all brilliant geniuses, all important, and all of which will get us absolutely nowhere in trying to understand the nature of atoms authentically. And you might think, okay, this is a basic high school course. Here is the new AP chemistry curriculum, which my exact words to them were, I'm going to make it my mission to make sure that nobody ever accepts this anywhere. I have been unsuccessful in my mission, but you can't read it, but in the box on the left it says a student, in order to do well on the AP exam, needs to be able to use experimental evidence to refine a model like the Bohr model. You can't refine Bohr's model. It's fundamentally flawed. It's not that the orbits are elliptical or sphere-shaped or what have you. There are no orbits, ladies and gentlemen. If you need a therapist, there are therapists on hand outside. We can talk to them later. There are no orbits. We've known it for years. On the right, we see electrons are in regions of space called an orbital. Orbitals are functions. Orbitals are math. Orbitals are a way of describing a function in phase space. And if you want to know more about that, take modern physics or come take my core class. It's going to be a lot of fun. So why won't the Bohr atom just go away? Well, you can't visualize quantum mechanics. I'm sorry to say that one of the big problems with quantum mechanics is you can't actually see something because there isn't a something, one something to see, and I'll talk more about that in a second. The math is hard. The math is really hard. In fact, if you want to do it really well, you got to take multivariable calculus, you've got to take differential equations, you've got to take linear algebra, all of which are great classes, all of which apparently you can get help on right here, which is really cool. And we have experts teaching them. But the bottom line is, for a novice to learn it, novice got to know a lot of math. And we don't necessarily want to wait till then. You can't learn quantum mechanics like you learn other things. Because when we learn other things, we use our perspective. We use our history. I learned yesterday how to walk, so running's got to be not so much harder. Walking and running are related. It's feet on ground. Quantum mechanics is not a thing. It's a whole new, different paradigm of how the world could behave. We'll talk about that in a second. And I think this one is one that I think is irrelevant, but certainly true in many people's minds. It would be very difficult to assess. That's a fancy word that educators like to use instead of test, because we know that people get upset when we use the word test, so we want to use assess. It would be difficult to assess these basic concepts given all of what I just said. And so the bottom line is quantum mechanics is strange and new, and quantum mechanics flies in the face of the perspective that we have, and it's much, much more comfortable for us to teach things orbiting things, or even if we don't teach it that way, maybe just to let people in the back of their mind still believe that that's the way it is. So here's the thing, guys. This is a particle. And I'm not going to belabor this point because the big buzzer in the front is about to go off. Those are particles, little red dots. And when you throw a particle at a slit on a screen, one thing happens or the other thing happens. It goes through or it hits the screen and it's blocked. And so you see on the far screen, the one all the way on the right, you have a bunch of particles that hit the far screen if they can get through the slits. This is what a particle does. That's the things that we're used to. If I throw my shoe that way, either the column blocks it or it's going to hit that poor dude in the head. I'm not a good shot, so you really don't want to take that bet. That's a particle. Waves are different. We teach waves. Don't worry, we teach waves. Waves are things that when they hit slits, they start to make diffraction patterns, right? These waves start to split off from each other and they interfere and they make a really weird pattern on the other side. We know waves. Anyone who ever took electricity and magnetism in high school physics knows waves. So we have particles and we have waves. Quantum objects are neither of these. That's the problem. A quantum object is not a particle orbiting a particle, and it's not a wave orbiting a particle. A quantum object is a superposition of states. A quantum object is something that hasn't yet decided how it will behave. And the worst part is, it doesn't make the decision how it behaves. You do. By making observations of it, by testing it, that changes it. When was the last time I threw my shoe and it turned into a wave? When was the last time you got to decide how things behave? A quantum object, this is a terrible representation, but it's the best one I've seen. It behaves kind of like an amorphous. It's kind of a wave. It's kind of not a wave. We don't know what it is. It's like some ghost out of some movie. It's going to kill somebody. I don't know. And when it finally hits the screen, guess what it hits the screen as? A particle. You know why it hits the screen as a particle? Because the only thing that could hit a screen is a particle. But if you took away the screen, you know what would happen? It wouldn't turn into a particle. And that's weird. So there are new tools. We have computers, thank goodness. We have computers, we have new tools, we have ways of trying to visualize this stuff. I just wanted to show a pretty picture from PNAS, this is Rhett, showing the first images of quantum atoms, which is kind of awesome. Again, here's the real problem, though. That's not an image of the atom. That is an image of what happens when we force the atom to choose. And it's, again, something we have to be very careful about saying because we're not seeing the atom. Here's a better view of the atom. An atom is kind of like a wave. And when that wave interacts with an oscillating electromagnetic field, that wave can change. And that change in the wave has an associated frequency with it. And if I say frequency, you might think wavelength. And if you might say wavelength, you might think light. And that's a pretty good explanation for what's going on with Bohr. Now, this is a one-dimensional example over here of I can't believe I'm saying this, but wait for it, 1s becoming a 2p orbital. By orbital, I mean wave function, and by wave function, I mean quantum object. So here's the bottom line, guys. I was lied to. And I don't think I was lied to out of malice or out of bad, or I don't think my teacher wanted me to feel this way. I talk to a therapist about this regularly. But you guys have a choice. You guys have the choice to recognize that when you guys are presented with new evidence, when you're presented with a new worldview, sometimes we have to abandon what we've seen in the past. Maybe we've done enough and it's time to start seeing the world differently. Heisenberg, he didn't know a lot about things, about particles, and he changed the world with quantum mechanics. What are you going to do? Good evening. We have time for a couple of questions, I'm told. Please. Yeah. I don't think you have a mic. Is there a mic? There's a mic. The mic is coming. Or maybe it's not quantum mechanics. That's not how it works.
Is it on? If Bohr knew that it was wrong as it was published, then how did it get past the paper that it was published in? And why did he publish it in the first place?
So first of all, publishing wrong things is not a bad thing, right? Because wrong just means we don't know what else to replace it with yet. Scientists are not infallible. In fact, we know that we're very fallible. He did better than anyone else. And if Bohr hadn't proposed quantization the way he did, it probably would not have led de Broglie to propose this idea, this insane solution of the wave function, or a standing wave for an electron. So we never know what's going to inspire others. And he actually got the right answers until you put it in a magnetic field. So he figured, how far off could he be? There must just be one other thing. Now that's one thing that we have to keep in mind here, guys. Sometimes one more thing that we need might be that one little tiny adjustment and then we're done. And sometimes it might mean that we have to throw out a field entirely and replace it with something tremendously different. You never know. I think we have time for one more question. Right there.
Hello. Okay. So the Bohr atom, it works well for some things, right? Like in chemistry when we're learning about ionic and covalent bonds. So maybe it's a good tool in the beginning, and then we evolve to something more complex like quantum mechanics.
I'm so glad you said that. The Bohr atom gets only one thing right, and that's the ground state hydrogen atom. So if you go to anything more than one single electron, Bohr gets it wrong. And the best part is, I was going to show you at the end of his paper, he says, hey, we can easily adapt this to 2 nucleus single electron models. No, he couldn't. No, you can't. Bonding doesn't work with the Bohr atom, and neither does anything with more than one electron. So it's a wonderful step in history, but we have to remember, and the fact that in high school you were allowed to believe that Bohr was this answer is either because maybe your teacher didn't know themselves. Unfortunately, only 35% of high school chemistry teachers have any training in chemistry whatsoever, which is a startling shocking figure. And second of all, you're right, it would have been very hard for them to teach you molecular orbital theory. I would have rather they taught you nothing. Thank you very much.